In this example, we're going to determine the magnetic field due to a current loop at some position z away from the current loop along the plane that goes through the current loop. So if we take a look at our diagram here, this is set up. I'm showing you the figure instead of drawing it out because it's a little more clear this way. So we have our current loop here, and looking at it, the current is going counterclockwise. So for the segment right at the top here, which we'll call our ith segment, the current is coming towards us, so to speak, or at least along the negative x direction. The current at the bottom of the loop, which we'll call segment J, is moving in the positive x direction. Both of these points are marked by the delta S vector, so delta SI for the top and delta SJ for the bottom. So that represents the length of the current segment and the direction of the current flowing through that current segment. For each one of these positions, so for segment I up here, there is an R hat vector with unit length, so with length 1, that points in the direction towards point Z, where we're evaluating this magnetic field. So if you use your right-hand rule, you can see that based on the current in the top of the loop here, the magnetic field would be pointing in this direction. So if you go ahead and take your right-hand rule, that's going to be pointing that direction again at point Z, and same for the Jth component. The Y components of these two are equal but opposite, so they will cancel. So we'll only be left with a magnetic field in the Z direction here. We've got some angles to note. The angle here, that should be in the, well, it's kind of in the XY plane for this part here. The angle between the R hat vector and the magnetic field here is 90 degrees. Same with for the J segment. The angle between the magnetic field due to the ith segment, the top of the loop, and the Z component of that is going to be this angle phi. There's also an angle between the Z direction here and the R hat vector. So that gives us the gamma angle there. Phi is also the same angle as the R hat to the y-axis over here. We have one last angle, theta I, so the angle between the delta S vector and the R hat vector is a 90-degree angle as well. So that would essentially be current going this way in the R hat vector. So all of these are at 90 degrees to each other.
From the figure, the magnetic field vector due to the ith component is an angle phi away from the BZ component. So we can write that as the BZ component of the ith magnetic field vector is equal to the magnitude of the BI times cosine of phi, the angle between them. And we can also see that the distance crossed with the R unit vector is going to be equal to the distance times 1, because the length of the R unit vector is 1, times sine of the angle between them, which is 90 degrees, so that's just going to be 1. The magnitude of the total magnetic field vector for the ith segment can then be written as mu naught over 4 pi I times delta S crossed with the R vector, R squared. Plugging in for what we just derived for the Z component of this, and accounting for the cross product that we've already gone through and solved, we get this equation. So again, this is the magnetic field due to one single current segment, the ith segment, in the z direction. So as before in early examples, we need to express our formula in terms of the variable that's being modified. In this example, that's going to be delta s. So we can go ahead and start with r squared is equal to z squared plus capital R squared, where z squared is the distance to point z, where we're evaluating this magnetic field, and capital R is the radius of our current loop. Now, it's easier to switch to z and capital R, even though they are constant for the example that we're looking at here. This way, if we want to change to a loop with a different radius or evaluate the magnetic field at a slightly different distance away, we won't have to go through and calculate how far away that point is. It'll be a little bit more straightforward. So this is slightly different than earlier examples. Now, if we take a look at the angles, phi and gamma, again, go ahead and take a look at the figure if you need to review what those are. Those are created by the magnetic field vector due to the ith current segment and the z-axis. If you notice, those two angles add to 180 degrees. Phi is also the angle between the r hat vector, and the radius r of the loop. So we can also write that cosine phi is equal to capital R, the radius of the loop, divided by r, the distance from the current segment to the point that we're evaluating, which we can now rewrite in terms of z and capital R. So plugging these two back in to our magnetic field equation for the zth component, so we've got mu naught over 4 pi, current times the radius of the loop, divided by the distance from the current segment to the point that we're evaluating, to the 3/2 power, times delta s, the width or the length of our little current segment. So now we can go ahead and start to take a look at integrating over all of these little current segments. So the magnetic field due to the entire loop is going to be the integral of all of these little current segments in the z direction only, which is, again, the same thing as summing over all of these little current segments. We can pull out all of our constants, leaving us with just the sum over the little current segments. We're going to assume that these get as small as possible so that we can integrate instead of just summing over those individual current segments. So if we take a look at the smallest distance we could travel around this loop is going to be 0. The largest length that we can travel around this current loop is going to be the circumference, which is 2 pi capital R. So that will be our limits of integration here. The integral of ds is just going to be s. And since we're evaluating it from 2 pi r to 0, this is just going to give us a 2 pi r. Again, this is capital R at this point. I can go ahead and cancel some things out. So I've got a pi on the top and the bottom. I've got a 2 on the top and the bottom. And I can go ahead and combine my r's. Okay, I'll go ahead and rewrite this. So we've determined that the magnetic field due to this current loop is mu naught, current in the loop, times the radius squared, over 2 times z squared plus capital R squared to the 3/2 power. Now if we examine this as z is much, much larger than r, so we're at very large distances away from this current loop, then my z squared is going to overwhelm the r squared on the denominator. So we'll end up with 2z cubed. So z squared to the 3/2 power gives us z cubed. If we evaluate this at z equals 0, so that would be the magnetic field at the loop center. And again, we're going back to the original loop equation, just evaluating it at z equals 0. That means the bottom part is all going to be determined by the radius, so that's r cubed. But we've got r on both top and bottom, so we can cancel some of these. So we get mu naught times the current divided by 2r. And if there happens to be more than one loop, we need to add the contributions to each of these loops. Up to however many of them there might be. If we evaluate all the loops such that they're centered at z equals 0, basically we have multiple loops, but these loops are very, very skinny, so we can essentially say that they're all in the same plane. Then we can evaluate the strength of the magnetic field at the center of that coil, so we'll call this coil center. That's going to be n times the magnitude of one loop evaluated at its center. So that's going to add an n to our above equation.